I know.
Okay, that's new. Sorry.
Oh, because it ends up
It ends up 2 to the right in the y direction. So,
right.
So you need to rotate about some axis in the middle,
Yeah.
or like the distance here is 1, right?
Mhm.
So if you rotate about this axis, you'll go 1 on this side.
And same thing there.
Yeah. I think this is like 1.
1B.
Yeah.
Right. So let me think about this.
Let's say the translation in the y direction was 3, right? Then you need to rotate by 1. The distance here is 1.5. When you rotate about it, the distance here is 1.5.
Sweet.
Yeah.
Yeah, so I thought, oh my god, the same thing, but what, how do you change it? Is that where it's free?
Talking about Q, yeah.
Q, so you take Q on the actual axis of rotation. This is just the vector to show.
Yeah, no, I got that. I got that.
So Q here would be like, Q would be
0, 1,
0,
0.
0, 0, 1, 0. Only 1 in the y direction.
Why? How do you know that?
Because we're rotating about this axis.
Because that's the only way you can tell.
Right?
That's not
But like, there's no way for us to move 2 to the right because, like, you see the axis of rotation is not the y direction. So you can't just use a screw.
Same thing about that. So the reason I can't let you go. Right. So we're rotating about them. Except for a Y. That's what and we end up in this direction. Here's 0, 2. When you rotate it, it's so weird to us.
Because, I
don't know why it's not
okay, so if this would make sense, right? So like if this was our original frame, what was he writing?
Oh,
Oh yeah, I'm just writing the end of this stuff. Okay, cool. So we should be good to get started. So just in terms of what we're going to talk about today, the main topics are inverse kinematics and these PK subproblems. And also, I have some stuff ready on Manipulator Workspace if you guys want to cover that. But if you don't, then we could always spend more time on the midterm. So just like as a quick show of hands, were you guys just rather do like midterm stuff or Workspace? Midterm. Okay, cool. Like that doesn't mean, that's not to say that I won't answer any questions regarding manipulator works. It's still absolutely one of those topics. Okay, cool. So we can start off with our subproblems, and then we'll go ahead and we'll talk about inverse kinematics to finish off the actual content section. Then yeah, we can go over midterm questions from there, either individually or as a group. Great. And then afterwards, if anyone has any questions about the workspace, then we can go ahead and cover that as well. Should be good. All right. Yeah, that's where we're going to start. All right, perfect. Alrighty, cool. So we're going to start out by talking about these PK subproblems. And inverse kinematics. Okay. So you might remember that last time we were talking about this forward kinematics problem, right? We gave this set of joint angles. We had like theta 1, theta 2, theta 3, so on and so forth. And using those joint angles, we wanted to figure out where the end of our robot would end up, right? So that looked a little bit something like this. Okay, I could just sketch out a robot arm over here. So we have one arm over there, and then we have a grip over here. Okay. So what we did is we went ahead and we attached a frame over here, right? We called that frame the tool frame, T, because it's moving with this hand, okay? And then we defined another frame over here that stays totally fixed in space. It never moves, okay? And we called that the spatial frame. So as this robot is going around, it's maybe rotating about this axis, theta 1, and it's rotating about here by this angle, theta 2, and this tool frame is moving with this robot arm as we're changing these angles, okay? So in general, what we wanted to find in this forward kinematics problem, is we were looking for the following transformation, GST of theta. So what we were looking to find was we wanted to figure out some way of getting between our spatial frame over here and our tool frame for any set of angles out there, right? For any values of theta 1 and theta 2. So we just represented that by this little theta over here, where this theta was just a vector of these values. Right? We just put theta 1 and theta 2 together in a vector just to stay organized. And we figured out that there was this great formula called the product of exponentials that allowed us to compute this really easily, right? So if we had some twist, we'll call xi1 representing our first axis, and some other twist called xi2 representing our second axis over here, what we showed last time was that we can represent this forward kinematics transformation by the following. So we have to the xi1 hat, theta 1, e to the xi2 hat, theta 2, times gst of 0. Okay, so this is the transformation associated with rotating our first joint. Okay, so rotate the first joint. This is the transformation associated with rotating our second joint. Rotate second joint. And this final transformation, GST of 0, this is what allowed us to convert from our tool frame over here to our spatial frame when all of our angles were still 0, right? When we were just in this normal reference configuration, we were like, hey, how do we get from T back to S? We use this GST of 0. Okay, so convert between T and S in the reference configuration. Okay, so the reference configuration is just when all of these angles are equal to 0. All right, so this was a transformation such that we were able to map between these two frames, right? So if we apply this GST of theta to a point in frame T, we know we're going to get back what that point looks like in frame S. All right, and this was something that holds. It's a formula that's valid for any set of angles theta 1 and theta 2 out there. Okay, so this was a super powerful formula, right? This was great. But in the real world, like a lot of the times what we're concerned with, it's not like going forwards in this direction. We don't just want to be plugging in random angles into our robot and then seeing where it goes. We might sometimes. But a lot of the times what we want to do is we want to have some sort of trajectory in space that our robot's going to follow. We're going to figure out the joint angles that will give us that trajectory. Okay, so now we're going to do this in reverse. So do this in reverse. All right. So what we're going to do is, instead of trying to figure out this GST of theta, given these theta 1 and theta 2, we're going to try and figure out theta 1 and theta 2, given some GST of theta. Okay. So now what we're saying is we're going to specify some desired transformation matrix between our spatial and tool frames. Okay. So let GD be the transformation we want between our frames. Between our S and T frames. Okay, so what might that look like? Well, in a practical situation, just looking at that robot that we drew above, maybe we want that going over there, that over there. Maybe we'll have something that looks a little bit like this, right? Our frame maybe will move over there, it might be rotated a little bit as we turn this around. That's going to be our tool frame, okay? And this is going to be our spatial frame. Once again, we have this theta 1, which is the amount that we rotated right there. And then we have theta 2. Okay? So that's just like that second cylinder, theta 2. Okay, so what we're trying to do is we know that at this point, we have this transformation between S and T is equal to GD, our desired transformation, all right? So we're going to figure out a way to work backwards to figure out what the theta 1 and theta 2 corresponding to this GD actually are. All right, let me ignore that. Oh, I'll be bored. All right, second time's the charm. All right, perfect. So what is this mathematical setup going to look like, right? So we know we have some transformation that we have desired between these S and T frames. And we know we also have a formula for the transformation for any set of joint angles out there, okay? So what we're going to do is we're going to try and solve the following equation, right? So e to the xi1 at theta 1, e to the xi2 hat theta 2 times GST of 0, right? We know that this is always the formula for our transformation between our spatial frame and our tool frame for any angle out there. And we're going to set this equal to this new desired transformation that we want to get back out from the system. All right. So this is our equation that we want to solve in the inverse kinematics problem. So inverse kinematics. All right. So what we're going to do now is we're going to solve this equation. This equation for angles θ1 and θ2. Okay. So we're plugging in a matrix that we want. We're plugging in our product of exponentials, and we're saying, all right, how can we somehow invert this product of exponentials formula to give us this matrix that we're looking for? Man, my computer really wants to update today. Okay, there we go. That wasn't blocking the screen for long, was it? It just popped up there. All right, perfect. Okay, fantastic. So where might we actually start out with? Yeah, it's probably calculus.
Like, update, is it Linux?
So I switched to Windows at the moment. Yeah. I've never been able to get into Edge. Yeah. All right, perfect. So let's try and figure out how we might be able to solve for θ1 and θ2. Okay. Let's think about some of the problems that are going to show up when we try to solve for these angles. Well, let's take a top-down view of our robot. So instead of looking at it from the side like this, we'll try and look at it from above. Okay. So let's say that this is our first joint over here, and it's going to be at this angle, that angle, and we want it to be at this final position right here. Okay. So our G desired will be taking us from over here back into our base frame. Maybe we'll have, okay, our basis vectors pointing out like that, and something like that. Okay. So this is our spatial frame, and then this is our tool frame. All right. So we're really just looking at the same problem from above, just looking right down on it. Okay. So what are some problems that are going to come up? Well, first off, something that we might notice is that our solution for these angles might not be unique, right? So solution for θ1 and θ2 might not be unique. And why is this? Well, if we have the following solution for θ1 and θ2, right? This is our θ1 right there. And then this is our θ2. We know that we could simply just reflect this across this line in the middle, right? We're going to get another solution, right? So if we're able to reach this position this way, maybe we'll be able to reach it that way as well, okay? So because of this, we often end up with a lot of different solutions in this case of inverse kinematics, right? This is going to be a problem for us. Many different solutions. All right, so what's another problem that we might encounter? Well, something that we see is that, even if we're trying to track the position of this point, right? We try to track the position of a simple point that is rotating in space in angle θ, right? Even if we know that this is L1, right? For given the length of that arm, we can use trig to show that the following over here, this is going to be L1 sine θ, right? And then this distance between here and here will be L1 cosine θ, okay? And what happens is when we add more and more of these arms, we're going to end up with these huge nonlinear equations in 3D, right? This is a 2D case, and we already have this nonlinearity that we have to take care of, right? Even when we're only looking at a single arm, right? So these equations are very nonlinear. Hard to solve. Okay, so what we need to do is we need to figure out a way in general to be able to solve these really hard nonlinear equations for these angles θ1 and θ2 for any orientation out there. Okay, so it's kind of tall order when you just say it like that, but it's what we want to do, and it's what we're going to do. So it's going to be pretty cool. All right. So our general strategy is we're going to try and break up these big complicated problems into a set of smaller problems, which you guys have probably checked out if you did the homework. So what we're saying is we're going to split up our overall problem into a set of simpler ones. That we know how to solve. All right, perfect. So what might this look like, right? How can we actually do that breaking up into simple problems, right? It's all very well to say that we're going to do that, but what are those problems actually going to be? So something that we might want to think about is when we're looking at a robot like this one, where can we view lab material? Just the lab specs. Oh, so the labs should be posted on the website, all the laptops. Okay. All right. So we're going to look at how we go ahead and edit this big complex robot so that it becomes simpler and easier for us to work with in this inverse kinematics problem. All right. So the first thing that we're going to do is we're going to look for a couple of repetitive patterns, right? We're going to see if we can break these bigger robots down into simpler robots that we know how to solve this problem for. Okay. So the process of breaking down big robots. Yeah, sure. Yeah, let me duck. Sure. All right. So what we're going to do is we're going to break down our large robots into simpler ones. Okay. So let's talk about how we're going to solve this inverse kinematics problem for a couple of really simple robot joints. All right. We're just going to look at basic 1-joint, 2-joint robots. We'll see if we can figure out a solution. And then once we've done that, we can go back to our bigger robots and see how we can piece these little ones together to get a solution for our whole. All right. So the process of breaking down these large robots into simpler robots is referred to something as the Paden-Kahan subproblems. All right. So I'm going to call them like PK subproblems, just for short. You could also just call them like subproblem 1, subproblem 2, but we'll talk about what each of those mean in just a sec. All right. So do we have any questions about our whole setup for inverse kinematics or anything like that? How do you guys feel? Cool. Yeah.
Not about the setup, but
Sure, yeah.
more like the immune constitution is first I think you don't need to calculate again like that end result, but how would you like you should calculate that?
Oh, right. So in general, you can leave these PK subproblems just in their form. So once you set up the PK subproblem, then you could be like, okay, I'm just going to solve this using PK1. But if you have a prismatic joint, for example, or a screw joint where you're able to exactly find the angle theta, then in that case, we'll expect you to figure out that formula for theta. So for prismatic, yeah, let me just highlight that. So prismatic / screw, find actual formula. So you find your actual formula. And then I'll do that later. Yeah. All right. So for prismatic or screw, we find the actual formula, and then for revolutes, you leave in terms of PK solutions. Okay. So you usually just split it into those two cases, and then that'll work out. Okay. Yeah. Yeah. Yeah, so it'll vary quite a bit for the prismatic joints. It depends on the setup of your robot, like where this joint is placed and whether you have any other prismatic joints in your robot. So if you have 2 prismatic joints that are parallel to each other, you're going to have infinitely many solutions for this. So let me just write this down real quick. So 2 prismatic joints that are parallel to each other, you have an infinite number of solutions. Okay. And the reason for that is that there's simply translations in the same direction, right? So if we're looking for an overall translation of like 10 in this direction, and we have 2 different ones that we can always change, all we need is that the sum of like theta 1 and theta 2 for those 2 prismatic joints is equal to 10, right? If that's our only constraint, then we have an infinite number of choices of theta 1 and theta 2 that'll get us there. Yeah. And then we'll talk about some other cases where we have like 1 and 2 solutions as well. I think I have one example. It's kind of a tricky one that I think is good to do that we'll do where we have 2 solutions for that. Yeah, sure. Right. Do we have any other questions? Yeah.
If those two are not on the same like axis, then do we still have infinite number of solutions?
You still have an infinite number of solutions. Yeah. So how do we find the actual formula for prismatic and screw? Yeah, we'll talk about that in a little bit. Good question. All right. Okay, perfect. So let's just review briefly the main subproblems out there. Yeah, sure. And then we'll go ahead and we'll see how they apply in actual problems. And if you guys want something that might be good, since I guess everyone's most likely done their homework, it might be handy if we just solve them all with a group. So you could just come up with like a clean and nasty looking example and then just figure out where to go from here if you guys want. But yeah, all right. So let's talk about the different subproblems. All right. So remember, we're trying to just break up these complex robots into a couple of simpler robots. Let's try and look at one of those simple robots, and we'll see what the solution might be. All right. So let's talk about subproblem 1. Subproblem 1. All right. And I'll just refer to this as PK1 for short. All right. So what we're going to do in subproblem 1 is we're just going to think about the simplest possible robot out there. All right. So think simplest possible robot. All right. So what this is going to look like is I'm going to have a joint right here, and I'm going to have my arm directly attached to that joint. All right. So what this is going to be is we're going to have a single angle theta, right? And just a single point P over here. So it's just one joint that's just rotating. All right. So we're just making this problem as simple as we can starting out. All right. So here's what we might want to do in an inverse kinematics scenario. So we might have some point over here. Let's call this point Q. Okay. And what we want to do now is we want to figure out how we can get to point Q by rotating this joint. All right. So we want to try and figure out how we can get point P to align with point Q by rotating this joint. What is that angle theta? All right. Well, let's talk about how we can set this problem up, and then I'll mention how this PK subproblem will solve this this whole thing for us. Okay. So we know that we can find a twist, which I'll call xi, for this simple revolute joint. Okay. And we know that the motion of this joint will be expressed by the matrix exponential, right? Like e to the xi hat theta will be the transformation of rotating this joint by angle theta. All right. So what I'm going to do is I'm going to apply this to our point P, because that's the point we're interested in moving. And I'm going to say we want to figure out e to the xi hat theta times P such that we get the point Q back out, right? Because that's where we want our joint to end up. Yeah, sure. So this is the transformation of rotating a single revolute joint. Right? So if we find a twist xi that's representing this joint, we just do e to the xi hat theta to represent this joint's motion. That's from like the product of exponentials. Yeah. Do we have any other questions about that setup? Cool. All right. So there's this guy called Brad Paden. He's a very smart guy, and he went ahead and he figured out a very nice solution to this problem. Okay. So we're not actually going to talk about the explicit closed form solution for this. It's basically just a lot of trig and a lot of just very funky tricks for solving this nonlinear equation. But what we need to know right here is that when we get an equation in this form, we'll always be able to solve for this theta. Okay. Or usually we'll be able to figure out what this theta is. All right. So this is called subproblem 1 or PK1. And we know how to solve this equation. How to solve this for theta. All right. So how many solutions does this equation have? What's the maximum number of solutions? Well, since we're simply starting at some point and rotating to some other point, right? If we're just excluding like repeat angles, like if we add 2 pi to that angle, we're just going to have a single solution for this case, right? There's only one way to rotate from some point to one other if we're just going about one axis. Okay. So we say that this has a maximum of 1 solution. All right. So this is our first subproblem. We're going to essentially take this single revolute joint. We're going to rotate it to this point that we want to be at using e to the xi hat theta times p equals q. And we're going to apply the solution of subproblem 1 to figure out what this theta is. Okay. Yeah. So we ignore like theta plus 2 pi, plus 4 pi, etc. Yeah. So we just consider like that single original angle theta to be our solution. Yeah. Did you have a question? Yeah. So this is like plus minus right there. Yeah, so it's like going around the other way. Yeah. All right, cool. So this is subproblem 1, right? This is a simple robot joint. We know that this is something that pops up a lot when we're looking at our questions, right? all of our robots are composed, or most of our robots are composed out of these simple revolution joints. So this is something important to think about, right? So this is a great solution, right? But a lot of the times we have something that is a little bit more complicated, and that is called subproblem 2. Subproblem 2 or PK2. All right. So what we're going to have now is another thing that you guys have probably seen quite a bit of. This is another pretty common scenario for us. All right, so we have one joint up there, second joint down here, and we maybe have like our arm coming off attached to that joint. All right, so now what we're able to do is we're able to rotate about 2 of these axes. All right, so we have one axis that's vertically and one that's going like backwards into the page. All right, so we have an angle there and we have an angle there. Let's call this theta 1 and theta 2. Okay, so in this case we have 2 revolute joints whose axes intersect. All right, so what we're doing now is we're taking a point P on the end of our end effector, right? And we're trying to move it to some other point in space, point P. Now, this point can be in a whole range of different places, right? It can be like backwards into the page, it can be out a little bit. We're not constrained to a simple plane because now we have these 2 degrees of freedom, okay? So now what we're looking for is 2 angles in this case, all right? So we're looking for the following. So we know that if we rotate it by a first joint, we'll end up with an e to the psi 1 half theta 1. Psi 2 half theta 2 from the second joint. So this one has it to a psi 1. 2. And if we multiply our point P by that, we should get our point Q back out. All right. So when we see something in this form, this is referred to as subproblem 2 or PK2. All right. So what we have is we have 2 revolute axes that intersect each other at some point that we're trying to get this point on our end effector to just another point within our reach. All right. So PK2 solves this problem for theta 1 and theta 2, right? So it actually gets both of them at once for us. It's kind of nice. So just to give you guys an idea of the different solution cases for this, I'm just going to redraw this thing that we're seeing right here in a slightly different format. And we'll see why a couple of the things that happen with this problem happen the way they do. Okay. So first off, I'm going to draw one joint over here. And then I'm going to have a second joint over here. All right, so let's say that this is, we call this side 2 and this one side 1. All right, so we're sort of taking like a front-on look at this right here. Okay, so what we're saying is maybe we're starting out with some point like P over here. Or let me move it further in over here. All right, yeah, so we're going to put our point P over here. And what we want to do is we want to figure out some sort of way to get that over here. All right. So we're moving from this point P in space to this point Q in space by somehow rotating about these 2 axes. Okay. So what I'm going to do is I'm going to sketch out what happens when we rotate this point P about our first axis, outside 2. All right. So just to give you guys an idea of what that looks like, it's sort of going to trace out like this circular path around this axis in space. Okay. So we're rotating about here. All right. Cool. So we might take it to say like somewhere like there, for example. Or do I actually want to move this over here? Yeah, here we go. Let me move this point over here, and then we'll be able to see it pretty clearly. All right. All right, perfect. So we see that as this is going around, with respect to this point of intersection, right, it's sweeping out this cone in space. So we're getting this cone that is going all the way around this axis. Okay, great. So we've done our first revolution. Now we need to go ahead and do our second revolution, right? So now, if we want to rotate this resulting point over here to get to our point 2, what we do is we take another revolution and we go around there. All right. And this is also going to be a cone. And it's also going to come down on this axis like this. Oh, draw that as a dotted line. All right. So what are our what are our theta 1 and theta 2 in this case? Well, what we're saying is maybe we're rotating about this first axis by theta 2 in this direction. Right? So maybe something like that. All right. So if we start over here and then we end up over there, right? This is our initial point. What we're doing is we're rotating around by this amount, theta 2 over here, corresponding to our second axis. And then on this other one over here, say this is where we're starting out with respect to this axis. What we're going to do is we're going to rotate around in this direction over here until we end up at our point Q. Okay, so we're first rotating around by theta 2 down here. Then we take ourselves around the second cone, rotate around by theta 1 until we end up at the point Q. Okay, so when you see this transformation, like e to the xi1 hat theta 1, e to xi2 hat theta 2 times our point P equals our point Q. All right, this is really what's happening. So we're rotating it about this first cone, we're rotating it about the second cone. So what does the solution mean in this case? Well, what the solution is we're looking for a set of theta 1 and theta 2 such that we get this nice intersection over here, right? If we get this intersection at this point, we know that once we start that second revolution, it'll be able to take us where we need to go, right? We've got to make sure that these two cones intersect, otherwise we won't get a solution. So the conditions for the intersection of this cone are what actually give us the number of different solutions for this P continuum. All right. So I'm going to sketch out like the top surfaces of these two cones, and we'll see how they intersect. Oh yeah. Yeah. Sure. Do we have any questions about this setup? Yeah. No, yeah, we're good then. All right, sweet. Okay, cool. So let's talk about the different solution cases. Solution cases. All right, perfect. So let me draw out part of this green circle over here and then our red circle. All right. So when these cones just touch each other at a single spot, right, like we have in this case, right over here, we know that there is going to be one solution. All right, there's a single theta that's going to take us over to this point, and there's a single theta that will take us over to solution over here once we get that person. All right, so there is one solution. Okay, because we're rotating around as intersection, there's only a single intersection, and we're rotating around to our final point. Okay, so when these two cones just touch each other just like that, we have one solution. Now, what about the case of two solutions? What does that look like? So now in this case, we have our same circle, and we're going to get something like that. All right. So now there's this kind of significant overlap in between these two cones, right? Like if one of these cones was tilted upwards a little bit more, we would end up with these circles intersecting each other in two different places. Okay. So we have two solutions, right? Because we can either go around our circle this way to get to this first intersection, and then go around this way to get out to our point, or we can come around our circle this way to get to this intersection, and then go back out that way. All right, so we have two different ways of going about this transformation to this other point. All right, so if we're starting over here, we can start out either going in this direction, we'll end up at this first cone, and then we'll go over there to our final point, or we can go around in this direction. All right, we can go towards this second intersection between the two cones, and then finish it out that way. So do you guys see how we did that in this two solution case? So what we're doing is we're taking these two cones, we're saying, all right, we're just going to squish them in a little bit more. They're going to intersect in two spots. So there's two ways to get to our final destination.
So it's not that you could go the other way, and that's what makes it the second one. It's
Right,
about
right.
the
It's about the intersection. So we're aiming for a different intersection entirely. Yeah. So if we just go around the other way, then that's the same thing as like subtracting 2 pi off of our answer, which really just gives us the same angle. So we only count that as one solution. Yeah. 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 All right. And then finally, let's talk about the case of zero solutions. All right. All right. So in this case, what we're going to have is we're just going to have no intersection between these two cones, right? If they never intersect, then there's never any way for our first rotation to get us onto the track for our second rotation. All right. So no intersection just means zero solutions. All right. So that would be, for example, if our axis was tilted further down, this first cone would just never intersect with the second cone, right? So there would be no way for us to get onto this second rotational path to get us over to Q. Do you guys see how that's happening? Or would it help if I did sketch? Yeah, sure. So let me actually sketch this out here, and then I'll show you what our problem is. All right, cool. So if our axis is now pointing down a little bit, right, like before it was maybe pointing over here, do that a little bit more like that. And let's say that our point is over here, right? And we want to bring it to over here. So first, what happens is we're going to trace out our same circle, right? We're going to go around this one first. And we're going to trace out this cone over here. Right, so we get our first cone. Great. But what does a revolution about the second sort of axis over here? What is this one? What does a revolution about there look like? Well, all revolutions that will end up at our final destination are going to look something like that, right? We got to start over here and we got to end up, you know, at this certain radius away if we want to actually hit that cone. Now, what we see is that there's no way we can rotate about this first axis to end us up over there, right? The closest we can get is maybe over here or over here, but that's not going to put us on the path to be able to intersect with that point by rotating about this axis. Yeah, so there are like 0 solutions. All right. Yeah.
Zero solution for using subproblem 2, right? Not that there are 0 solutions generally.
Yeah. So for subproblem 2, there would be 0 solutions for this case. You might have to take another approach, or yeah, it might just geometrically work out that your robot couldn't meet this certain configuration. Yeah. Yeah, let's see.
It depends on the point chosen, right? Like,
Yeah. So like if we aim for a point like all the way over here, right? So let's say that this is like somewhat on like this arc over here and something like that. So all the points we're going to be able to reach will fall within this sphere. If we just pick a point that's outside of that, there's no way we'll be able to reach that. And then we'll end up with this case where Q is just like too far away from this axis for us to reach by a certain rotation about this person. So if I put Q like super far away over here, that's sort of what we're doing in that case. So we're just saying our robot arm is not ever going to be able to reach that point by doing one of these rotations. Oh yeah, let me see. So I guess we would have yeah, so this is our so if we had an axis that was pointing like that. Oops. Yeah, so this could be like our first axis for looking at our robot front arm. And then our second axis would be something like that. So we're like looking at the front of our robot, and then our hand is, I guess, like pointing over here to start. We want our hand to end up over here just by rotating backwards in this direction. So if we draw this in 3D, this is going to look a little funny, but let's see if we can pull it off. So maybe it'll look something like this. And then we have that over here. And then maybe our arm is like reaching backwards in that direction, right? So it's going to be going along like that in space. And we want it to go to this point over here, right? Which is like further out towards us. So this is our coordinate frame over here. And this point is like all the way in this position on our coordinate frame. And this point is a little bit down. And yeah, sure. So maybe it's like towards the back and then down like that. So if that's like back into the page and this guy is out front of the page, then this arc will never intersect with, you know, this arc over here. So then that's kind of what we're seeing over there. It's a little weird to visualize when it's like skewed sideways like that, but you sort of see like where this point comes in. It's like we're taking this guy over here, and then all of a sudden we're like looking at it at an angle from the side. And then that gives us this 3D picture instead. Does that make sense? Or okay. Yeah.
I just like maybe a clarification for subproblems. So
Yeah.
For there to be a solution that exists, it has to be a point that exists that can be defined by both individual organizations.
Yeah. Yeah, so for example, if we just put this point like too far away or like too close in, for example, then we might not be able to reach it because these cones might not intersect.
So both of themselves are both together. Like both angles like that point has.
Oh, yeah, so there's both angles together conics.
Okay.
So we're looking for a combination of angles that'll get us there. And if there's no such combination, then we just say there's no solution. Yeah. All right. Yep. Yes. In this case, I believe there would be only one solution. Yeah, so if we pick P and Q actually as the same distance away from these axes, here, so if this distance, I'll call that D. If that's the same as this distance, we're always going to have one unique solution. Yeah. And if like, oh, so it's also that, and then their distance from the axis of rotation, I call that D2 and D2. Those should be the same. And then just by trig, we'll be able to show that they'll have to intersect at the same. Does that make sense? Or I don't know, how does that look?
That's the radius.
Yeah. So their distance to the axis of rotation needs to be the same, and their distance to the point where those axes intersect need to be the same. Yeah. Yeah. So right. Yeah. So it's going to happen when those two cones are the exact same, basically. Yeah. All right. All right. Do we have any other questions about subproblem 2? Cool. Okay. So finally, the last one we're going to talk about is subproblem 3. All right. And I also just write this down as like PK3 for Paden-Kahan 3. All right. So far we've been talking about, yeah.
Sorry,
Sure.
not off topic, but have you ever gone over like the actual process of eliminating?
No, yeah, we're gonna do that after this.
Okay.
Yeah.
All right. I just didn't know.
Yeah, no, we literally just started here just to show you where we began. We just did like a little review for kinematics, and then we just started talking about like why we want to do this problem.
Okay.
Yeah, sure.
Yeah. Not our questions.
All right. Were there any other questions? Okay. Oh, yeah.
No. Yeah, no, before that. Okay, so it's 0 to 0. Okay, thank you.
Sure. Yeah. All right. So for subproblem 3, what we've been talking about so far is we want to go from one point to another, right? We're specifying these actual points in space that we care about. But what we want to do in the case of subproblem 3 is a little bit different. Instead of just specifying these actual points, we're going to specify a distance that we want to be from something. Okay. Let me show you what I mean by this in just a sec. Okay, great. So here's what we want to do. Once again, we just have our single revolute joint. All right. So make sure that you know this is not for prismatic joints, not for prismatic or screw joints. Okay. So let's talk about where the subproblem 3 comes up. Okay. So let's say that we want to have our arm reaching out here at a certain angle theta, right? Let's just say that this is some configuration that we're at. And let's say that we have a point Q over here. All right. And let's say that we want to be some certain distance from this point Q. Okay. So imagine that we want to be a special distance delta away from this point Q. Now, how do we ensure that this happens for this certain angle, right? Like, what is this angle that makes sure we're going to be this distance delta away from Q? How many angles are there that allow us to do that? What's going to happen? All right, so let's frame this problem mathematically. We know that this point P, when it's rotated by angle theta, will end up in the following position, right? So we have e to the xi hat theta times P over the action of rotating this point P around this joint, okay? So that's going to take us over here. Now we want to subtract off this point Q if we want to find how far away we are from it, okay? So we're taking e to the xi hat theta, we're subtracting this point Q, and if we want to find how big that difference is, we're just going to go ahead and take the magnitude of that. All right. And we're saying that we want the distance between those to just be this amount delta, right? Delta is just any scalar number. It could be 0, it could be 1. As long as it's greater than 0, we're all good to go. Okay. So what subproblem 3 does is it tells us how to solve this equation, right? So PK3. So how do we get theta such that P is distance delta away from Q? Okay. Yeah.
Just to understand something, P should technically be the point before rotation.
Oh, yeah, excuse me. So if P is like our original point over here, we're taking it to this point P prime after rotation. Yeah, that's a great point. Yeah, so it'll be such that P prime is this distance delta away from Q.
So how do you find
So this one is just P, since our original rotation is to act on P to get us to this point P prime.
oh,
All right. So yeah, in general here, what we're doing is we're saying, all right, we're giving it this point, we're giving it this other point. We want to make sure that we're a certain distance away from it. How do we make that happen with our choice of angle? Okay, so that's what subproblem 3 is. Now, how many solutions does this have? How many solutions? Well, let's take a top-down view of this once again, and we'll see if we can figure out what's going on with the number of solutions in this case here. Okay, so what I'm going to do is I'm going to draw out, this is the top of my axis, just this thing over here, that one. All right, and we have our end effector. It's an angle theta, right? And let's say that at this angle theta, we are the correct distance delta away from our point. So if this is our point Q, and that's our point P. Let's say that the distance between them is delta. All right. So this is one configuration that makes it work, right? We're at this correct distance delta. Now, what's going to happen is, what if I do something like this? What if I bring this over here?
Sorry, is that P or P prime?
That's a P prime. Yeah, thank you. Yeah. So yeah, this would be our original point. P. Yeah. All right. And then let's say we have some other point over here, P double prime, right? And this is going down the middle. So we can actually find a second angle theta, right? Theta prime, that will take us to this other point, which is also a distance delta away from it, okay? So because we can always be symmetric about this point that we're aiming for, we can get two solutions when we have a point that looks a little bit like this, okay? So symmetry gives a maximum of two solutions. All right, so this isn't actually always going to happen, right? This is something that depends on the choice of our point delta, or the point Q and the amount delta that we're looking for. So for example, if we want to have no solutions, suppose that we have the following scenario, okay? Say that we have our robot arm over here, where this is our original point P. Let me just redraw that a little bit straighter over here. So this is our original point P sitting right there. And let's say that we have our point Q right on our axis, okay? Now here's what I'm gonna do. I'm gonna say that the distance from P to Q, so P minus Q, which is the length of this arm, right? So the length of this arm will be, let me call it 10 meters, okay? It's a really long robot arm. But let's say that the delta that we're looking for is 5 meters. But we know that no matter what theta we turn this to, right, we're always going to be 10 meters away. We're just going to be tracing out this circle in space. So if we're requiring this 5 meter distance and we're always going to be 10 meters away, there's no way we can ever have a solution in space, right? So we'll always be 10 meters. So away. So there is no solution in this case. All right. Do you want to? Yeah. Okay. Good.
So this no solution is based off data, based off
Yeah, so it's going to be based off of the point Q that we're choosing and based off of the delta that we're choosing. So this isn't the only case where this happens. Like for example, we could pick another point like over here, like a point Q that's like, I don't know, like 15 meters away. And we could say we want to find like a delta that'll make this like 1 meter away. That's not something that we can do, right? There's no way we're going to be able to extend this arm 1 meter away just by rotating. Yeah.
For the case where Q is equal to the points,
Mhm.
so if Q is delta is equal to L,
Yep.
then it does not mean you're infinite.
So if delta is equal to L, then yeah, we have infinite solutions in that case.
Then it's like greater than 2 so maximum.
Oh, yeah, okay. Yeah, so I guess we generally sort of ignore this case where it's on the axis because it gives us some kind of silly stuff. But yeah, I guess, yeah, like barring this kind of example, we have a maximum of 2 solutions usually. Yeah, great point. All right. Yeah.
Discussion of the materials possible.
It says 4 solutions.
What is that for?
That's the answer to one of the questions.
Oh, yeah, it might be the answer to one of the questions involving a
It might be like the whole.
That's the whole amount.
yeah. So if you multiply like 2 by 2 for 2 joints, then you should get 4. Yeah. Yeah. Mhm. Yeah. So if we had another one that's moving us into and out of the paper, like something like that, right? So we're like going along like that direction or this way. Like, is that what you mean?
Or like looking at the top down view.
Right.
You pointed
Oh, like straight like into the page, like that.
the one above.
This one?
When you want two solutions.
Oh yeah. Yeah, like we're
So you have things on the left and right side. of the view, not like the bottom and left.
yeah. So that's an interesting point. It's just that the thing is in this case, we're just restricting ourselves to like one rotation. Yeah.
But this is like adding to.
Right. So just when we're looking at PK3 all on its own, we're only considering the single axis of revolution. So we're not thinking about this.
Yeah, so with PK3 is there no way to actually move the arm to point Q?
Which one? Yeah, sure. Mhm. Yeah, so that's when we have no solutions in that case. Oh, so yeah, if you picked like delta equals like 10, then in that case we would have infinite solutions. Infinite solutions. Because that way the distance between these points is already 10, right? So if we're just moving around the circle, then we can have an infinite number of solutions. Yeah, in that case we could just pick any angle out there and then that would work for us. Yeah. Did you have another question? Dan?
Oh, no, I think it was just
Oh, okay. Sounds good. All right. And then finally, we can talk about the case of.
That's not a good one, right? We don't want.
Yeah. Yeah. So usually we try to pick our points to make sure that these infinite cases won't happen because those really aren't super useful for us when we're trying to find like a set of theta values. So, yeah. All right. So if we think about a case where we have only one solution, we could have something like the following. All right. So we could have. Redraw that. Let's say we have something like this, and we have our point in our initial configuration, something like that, right? Let's keep this axis extended out, and here's what I'm going to do. I'm going to pick this other point Q right here, and I'm going to have it such that the distance between the two of these is equal to say like 1 meter, for example, right? So in this case, if the distance is 1, distance equals 1, and the delta that we're looking for is also 1, we have a single solution. For theta, right? In this case, theta equals 0 is the only thing that's going to get us that 1 meter requirement, right? Like if we move over here, we start moving away, and we end up with some different value of delta between the two of these. Did you have a question? Okay. So we can also end up with, just this simple theta equals like 0 solution, or if we had another thing like this, where we have our point P and then our point like Q over here, right? and that was also 1 meter, we would also end up with a single solution value for theta in that case. And this pk2 will give us, this pk3 will give us the solution for that theta in all cases. Okay. So when we just have this q like coming radially outwards like that, and it's beyond the maximum reach, then we're going to end up with this single solution. Okay. So if q is beyond the maximum reach, and delta is appropriately chosen to be the distance to like this little circle over here, right? It's chosen to be like this distance over here to the circle. We have one solution. Okay, so those are the 3 different cases for this subproblem 3. They're a little bit more subtle than the cases for like these other subproblems that we talked about. They require like really some edge case kind of thinking. It's not really so nice like the other ones. We see these codes intersecting. Here, it's really just we're making up cases to make this problem screw itself over. Yeah.
Why should I want to have it beyond reach, like to guarantee a unique solution? Or?
Yeah, so that's not really something that we pick in general. It's just something to be aware of when we have like these sorts of problems. Yeah.
They don't hit the computer and they
Yeah. Yeah, so like a lot of these values, like no solutions or infinite solutions, we avoid picking those points to end up like with these sorts of problems. So like for pk1, for example, if we pick the points to be like the point on our axis, right? If we pick point P to be the point on our axis, in this case, we want to end up at subproblem 2. So if we pick like a different P, like P2 over here, and then we also pick like a point Q2 over here, where they're both on the axis, then we end up with an infinite number of solutions, since any rotation will just keep it directly on the axis. So we just avoid picking points like that to avoid causing these problems for ourselves. All right. So those are the 3 main subproblems, right? We've taken our more complex robots and we've broken them down into these 3 different cases. Sometimes where we have a different shape for our robots, right? We have 1 revolute joint versus 2 revolute joints, and sometimes just where we're looking for something different, right? A distance between 2 points, or maybe just that point itself. All right. So those are the 3 like PK subproblems. Now, if anyone, has any questions, let me know. Yeah.
all the way down.
Oh, okay.
Yeah, thank you.
Sure.
The P is our starting point.
Yeah. So P is like a point on our gripper, or it's just any point on our robot. So P prime is where it ends up after we apply this robot transformation to it. Q is just some point that we want to end up at, or we want to have some constraints around it. So all these points we're picking pretty much totally arbitrarily. Yeah, so Q, for the case of PK1 and PK2, Q is this point where we want to end up. So we want to figure out some set of angles, theta1 and theta2, that'll take us from our original point P over to Q. So we want to make sure that P prime and Q will match up with each other. Yeah. But in this case of PK3, we want to make sure that P prime and Q will be some distance delta away from each other instead. Yeah. 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 So in a lot of these problems, what you're going to say is all right, I'm going to pick this point such that it's within this zone or it's on this axis. And then based off of that point that you pick, you're going to end up with one of these special cases of these problems. Yeah. So we'll talk about how we do that in just a sec. Right. So could I explain the maximum 2 solutions case again? Oh, yeah, sure. Yeah, so basically what's happening in this 2 solutions case is, here, let me try this. So let's say that we want to be like a distance delta away from our point, like our desired point Q over here. And one way we can achieve that is by moving our robot arm to like this position, where we have like this point P, right? But we know that another way that we could be a distance delta away is just to do the same thing, but on the other side, right? So going to be distance delta away, right? This is like approximately the same distance as that just in my sketch. And I'm just drawing it as this arm is going like over here instead. So we have this symmetry about the center line between our point P on, or our point P and our point Q on either side, right? So we can go on one side and get our distance delta, and go on the other side and get our distance delta as well. Did that answer your question? Oh, okay, sure, yeah. Yeah, was there another question? All right. Yeah, yeah.
So are you gonna go over like examples?
Yes, I'm gonna do a couple examples and then.
Okay, I was just wondering, so there was also a question on homework and discussion.
Yeah.
Where like they give you some rotation matrix, right? There's actually two rotations, like one about x-axis and the other one.
Right.
How do you know that, like if it's with respect to the roll frame?
Oh, yeah, sure.
Did they tell you that?
Yeah, so usually they'll tell you, but if you see something like if you have like an RZ of like pi times RX of like pi over 2, like something like that, right?
Right.
Yeah. So first what you're going to do is you're going to apply RX in the growth frame. And then what this is going to do is it's going to transform you into a new frame. So then this RZ, here. Yeah, so we can actually, yeah, let me just sketch this out in this piece over here. Sure, yeah. So we have like X, Y, and a 0. Right. So what we can do to figure out where this is going is we can apply this to like each of these basis vectors over here, right? So if we want to figure out our next frame, what we can do is the following. So this is going to take us over to so we're going to have Rx of pi over 2 times our original X, right? Because X just stays the same in that case. And that's going to be a rotation around the other direction, actually. Yeah. So then we're going to move Y up over there. Y up. And then we are going to move Z over there. Okay. So then what we've done right here is we've taken this point X, right? And we've rotated it by pi over 2 within the spatial frame. Okay. So since we're multiplying it by these vectors in the spatial frame, these ones are also still in the spatial frame. Okay. So we're treating this rotation like a physical rotation of these vectors in the spatial frame. Yeah, sure. So when we apply Rx pi over 2 to something in our initial frame, it rotates all vectors by pi over 2 in that frame.
Oh, so we're still assuming, it's like with respect to a fixed frame?
Yeah. So in this case, it would be with respect to the fixed frame. And that's because we're using this interpretation where we're multiplying, these transformation matrices by these X, Y, Z vectors to get, what happens to those vectors after we do this rotation. So we're not thinking of it like a change of basis in this case between two frames. We're thinking of it like an actual physical transformation of these vectors. So yeah. Yes, and then we end up with this. And then when we do RZ of pi, I believe, yeah, we would just end up rotating like about this axis right over here. And then, yeah. Yeah, exactly. All right, cool. Do we have any other questions about this general subproblem stuff before we go on to our other example? Yeah. Yes. Yeah, so that's actually not defined as like one of these subproblems. So all of these subproblems are only for purely rotational motion. So they're just for joints that revolve. So in the case of a prismatic joint, we can a lot of the times find a unique solution. And that's something that we're going to have to find an exact value for instead of just saying we can apply this. Yeah. All right. Okay. So we can do alrighty. Oh yeah, thank you. So do you guys want to, I don't know, like how are we feeling about something? Do you want to do like a hard problem and then we could just come up with a couple of bad problems? Yeah.
Can we just do the homework problem?
Yeah.
Like homework like number 2?
Yeah. Let me actually pull up what that was. Okay. Yeah, so we get the spherical one on the end and then a prismatic joint. And then
And also, if someone asked them in the chat.
yeah. Yeah, so actually, we can just replace the prismatic joint by a screw joint here. Let's see how that goes. All right.
Wait, what? So like, you don't have to solve for the.
It's going to be pretty much exactly the same. Yeah. So the reason is that the prismatic joint is the only thing that's giving us this translation in a certain direction, right? And since it's the only thing that's giving us this translation, we know that we can solve for it in terms of that amount that we need to translate directly. So we're really treating it the same as this prismatic joint because it's the only thing that's giving us that sort of outwards motion.
But have you solved for the rotation with like in terms of like the like they call it like max?
Yeah.
In terms of max or zero.
Right. Yeah, so that's a good point. Basically, the thing is that the twist xi that we use to represent that will actually be, I guess, like it'll take care of it for us in that case. So we're sort of abstracting all the information about what this thing is doing just into that twist. I think like xi3 in this case. So that thing's actually just going to do like everything we need for this twist, and it's going to be the same thing. It's just like substituting directly into the prismatic. Yeah, it's kind of nice.
Yeah, just not. This is like how is you find? Just a bit.
Yeah. Okay. Sure. Let's see.
Yeah. So if there anything getting out of the coach at the beginning of the game. Yeah. And there would be topic, which is subscribing to your published. It's a subscribe. That one is gonna you have to put it together. Make it your own. You have to remember that.
Yeah, so I'm gonna draw it in just a sec. So usually you just put like these little things over it to indicate that there are threads. So just draw like these little loops across it, and then you should be good. Hey, how's it going? Nice. Great.
Get a bigger room, eh?
Yeah. Inside two. Are there extra chairs? Oh, there's the one in the door. I think it should be okay. Yeah, go for it. Oh yeah, are you using yeah. I don't know if it's gonna push you across the floor or anything. Is it okay? Yeah. Okay, cool.
Yeah, or somebody's been dropped the baseboard over rather than. Ooh, that's an this is good.
This is good. All right, sweet. Okay. Yeah, so we had xi1 there, xi2 there, and then like xi3 was that one, theta 3, and then do you guys remember which one was 4, 5, and 6? I think this was 6, right?
Yeah.
Xi6.
Where was up?
Okay. 6.
Was up.
Okay. 4. Okay, perfect. All right. Xi4. Yeah, I mean, there's only so many combinations of these that we can do here.
Oh, you're right. I'll be quiet.
All right, cool. Okay, so let's see. Start at and that is a pitch. Alrighty, cool. So I guess in terms of the solution for this problem here, so Sorry, that's an H right there. So what we've done here is joint 3 is a screw joint. Screw joint with pitch H. Yeah. So all we've done is we've taken our prismatic joint and we're like, okay, we're going to do this now instead. All right. So the main thing to keep in mind here is that since this screw joint is the only thing that's pointing in this outwards direction, we'll be able to find a unique solution for what this value needs to be, right? Like nothing else will be able to take this and move it over here, right? The screw is the only thing that's giving us the power to translate along here, all right? So if we give it a desired point, like or a desired transformation GD that'll take us to this point, we know that the screw will be able to give us a unique identification of what that is, all right? All right, so the basic idea is we treat the screw joint like it's prismatic. Okay, so now the only difference here is that instead of translating distance like theta 3, like a prismatic joint would, now for a screw joint, theta 3 is actually representing our angle of rotation, right? So the distance we're translating is the pitch H times that theta 3. Okay. So that's the distance that we translate. So just remember, pitch is this conversion from the angle we're rotating to the distance that we translate for a screw joint. All right. So all up, what is our product of exponentials going to look like? So we start out by writing the product of exponentials. Product of exponentials. Okay. So we're going to have e to the xi1 half theta 1, e to the xi2 half theta 2. Bear with me for just a second. xi2 half theta 2. Theta 4, e to theta 5, e to xi6 hat, theta 6, and it's going to be times some GST of 0, and we want that to be equal to our G desired, right? This G that'll maybe take us to a configuration over here, or maybe over here, G desired 2, something like that, right? So it's just this arbitrary matrix that's within the robot's reach that we're given. All right, we're going to end up here something. Okay. So what we're going to do is we're going to take this formula and try and isolate it so that we get all of the angles on their own, all right? Because these angles, you know, they're what we want to be solving for in this case. If we're not able to get the angles on their own, then we won't be able to solve it, okay? So the first thing that we're going to do is try and bring this GST of theta over to this side. And this is something that we can do because we know how to solve for this GST of theta, right? So I think in this problem, we put the tool frame right over here, right? So that's your tool frame. And then, where was the base frame? Was it over here? This one? Yeah. Oh, it was the bottom. Okay. All right. So that is your spatial frame in that case. All right. So we know that just using our methods from forward kinematics, we're always able to solve for what that GST is, right? We know the rotation between these just by inspection in the reference configuration. We know the translation also by inspection in the reference configuration. Okay. So since this is a totally known matrix, we know how to take the inverse, right? Take the inverse. So we're going to multiply both sides of this by the inverse of this matrix. I'm just going to copy and paste this down so we just save the line. Yeah.
I'm slightly confused as to why we don't put the key at the end effector and there's some space between the end effector and the joint.
Yeah, that's a really good question. So the main reason for that is that it essentially will help us like cancel out some of our axes right here. So if we put our end effector right over here instead, then what we're looking for in this forward kinematics problem, it's always a transform between S and T, right? So if we put T on this joint instead of this extra little distance over here, we won't need to account for that extra length between the hand and this tool frame, right? Like we're just pretending that this is the only one we cared about. So I think in the first part of the problem, the reason that we did this was so the reachable workspace and the dexterous workspace would be the same, right? So if you put it over here instead, then it wouldn't be. But since we have it, you know, just directly on the center of these joints, it's able to have any different orientation in this tool frame at the end. Yeah, sure. All right. So we're just going to multiply by the inverse on both sides. And let's see what that gets us. Okay. So it's just like we're doing multiplying this side by GST of 0 inverse equals GD GST of 0. inverse. Right? So this is just going to cancel out and become the identity. So I'm just going to erase this right here, so you don't have to write it on a new line. Bring it up. Okay, cool. So something that we can do a lot of these problems just to make our lives easier is that we can relabel these large products of matrices on the right-hand side. All right. So GD GST inverse of 0. I'm just going to call it G just for short, so we don't have to write that thing out every time. Okay. Yeah. So geometrically, it doesn't quite mean anything. Like it's not really something that we have to interpret. It's just something that we know the value of, and we know that it's equal to the left-hand side. Yeah. So all the stuff on the right that you'll see is the stuff that we know how to calculate at the moment. There's no unknowns over there. Yeah, good point. All right. So we know this matrix. Okay, cool. So the first thing that we're going to do is we're going to try and figure out how we calculate this screw joint, right? So something to keep in mind here is that this screw joint, it's something that both rotates and translates, right? So we're rotating about this axis over here as we're going along. And we're also translating along this axis. But when we look at this, what we see is that we also have this xi6, right? That's rotating parallel. So any rotation that this screw axis will do will be parallel to this other axis of rotation that we already have here, this other xi6. So that means that all we really care about in this case is the amount that this thing is translated, right? Because we know that any rotation that happens because of the screw joint, we can just undo with the help of this xi6, right? So we really don't care about the screw property. We can just think of it exactly like the same prismatic joint that we were dealing with before. All right. So you see how this screw joint are both like rotating and translating along here. So we're like rotating about this, and we're also translating along. When we look at this xi6 that we have at the end, that has the same exact axis of rotation, right? So any rotation that the screw joint does, we could just undo with this xi6 later on.
Is that because we have them pointing in different directions, but it doesn't matter?
So in this case, they were pointing in the same direction, right here, right?
So Taylor 3 is this way, and Taylor 6 is this way. The arrow, I mean.
Oh yeah, the arrow doesn't make a difference. Yeah, so we could just flip like the sign, and then that would take care of it.
Okay.
Yeah. So
Same axis of rotation, one can undo the other.
yeah, so for that reason, we don't really care about this extra rotational effect. Now, something in general is that if we don't actually have that condition where we have like these two rotations, then we might end up with some case in practice where there's no solution, right? Where there's no angles that will give us this desired matrix that we want. But this isn't really something that we are caring about, like when we're just giving you these problems. The actual process of solving for this inverse kinematics will be the exact same. We're not asking you to guarantee a solution for everything out there, right? We were talking about those cases earlier where you have one solution or zero solutions. We know that we might have those for some choices of matrices, but we're just saying, all right, we're going to live with it and we're going to get what we can. Okay, cool. So are there any questions about this setup that we've done before we actually go ahead and solve this problem? All right, cool. So in general, whenever you see a screw or prismatic joint, you want to solve for those first. Solve for these first. And the reason for this is that a lot of the times in these problems, this is sort of low-hanging fruit, right? Like if we look at this case right over here, and we know that we want to translate out to this direction, right? We want to be like moving in that direction. We already know that this screw joint is going to be the only thing that's capable of moving us outwards in that direction, right? All these other ones are just revolute. They're not going to be able to actually extend our arm. So for that reason, it's oftentimes a lot easier to start out by solving for these, screw or prismatic things, because they give these motions that these revolute ones simply aren't capable of doing. Okay. All right. So solve for these first. So when we take a look at our whole product of exponentials formula, right, this whole thing that we just derived, what's a problem? Well, we know that this joint over here is our screw joint, right? So if we want to figure out what our theta 3 is, we somehow need to figure out our way to get from here all the way into that point, right? Because at the moment, if we apply any point to this, right, any point P, the first thing that we need to do is multiply it by e to the xi hat 6, theta 6, but we don't know what that is, right? So that's not something that we could do yet. So we need to find some way of knocking out these three over here, some way of getting rid of them so we don't have to worry about it, okay? So what I'm going to do is, here, let me get get like a cleaner version of this because there's a lot going on in this picture. Whoops. All right. All right, so I'm going to copy this and then just put it down there. All right, perfect. Okay, perfect. That's I6. All right, great. So, oh, let me just redraw these threads here. That's fine. Yeah, if we see a squiggle, we'll know what you mean. Yeah. All right, cool. So this is this distance h theta 3 that we're transiting. All right. So in general, how are we going to knock out these different terms, right? What I'm going to do is I'm just going to go ahead and copy this whole product of exponentials formula from up here. Copy. And sorry about all the copy and pasting. There's so much to write in these ones. All right. So I had 6, theta 6 is equal to this matrix G on the side. All right. So something that we know is that if we apply a rotational transformation to a point on the axis of rotation, it's going to do absolutely nothing, right? Like if I have this axis in space, omega, and I take a point P on this axis, and I rotate this point P about this axis omega by some angle theta. No matter what that angle theta is, right? We're already on this axis. It's going nowhere, okay? So if we rotate a point already on the axis, nothing happens, right? Nothing happens. All right. So now with this fact in mind, let's take a look at this problem and let's see if we can figure out any good point to multiply this whole thing by that will be able to knock out these terms over here. All right. So the first thing that we do is we take a look and we see, okay, is there any points where these axes are intersecting? Is there some way that I'll be able to knock out all 3 of these at once? Well, we know that they will all intersect at this point right here, right? Xi4 is coming down, Xi5 is coming in, Xi6 is also coming in, right? So I'm going to label this point PW, just for wrist, okay? What I'm going to do is I'm going to multiply both sides by this point PW, all right? Now, since this point PW is on the axis of all these different twists, you know, Xi4, Xi5, and Xi6, we know that since these are revolute joints, when we do all these rotations, they're not going to do anything, right? It's the exact same as this situation up here. So for that reason, we may as well just not even include these Xi4, Xi5, Xi6, right? We know they're having no effect on this point PW, so we don't need to write them there, okay? So that knocks out all 3 of those for us. So now we're just left over with e to the Xi1, theta 1, e to the Xi2 hat theta 2, e to the Xi3 hat theta 3, multiplied by that same point PW, because it hasn't been transformed at all, no matter what these angles are, is equal to that matrix earlier we defined G times that same point PW. Okay, so does anyone have any questions about what we did there? Yeah.
Let's double check for what happened to the point that's like in the absence of the right rules of transformation, because you can't like remove the left.
Right, right. Like we can't multiply by a point over there, for example.
Okay.
Yeah. All right. Do you have any other questions?
But that's because matrix multiplication is not coming to.
Right. And yeah, also the sizes like wouldn't work out in that case. Yeah.
Make sure P and the unit is not
So P, oh, sorry, yeah, like a P. Yeah, so it doesn't actually matter that it's on the axis as I3 in that case. So that's only something that matters for the case of these pure revolutional like motions. But if we have something like an axis of translation, like a V right there, and we have a point on that axis, the point P, and we translate it along that axis, we know that despite it being on the axis, we can still translate it along that thing, right? So it'll be affected by translational motions along that axis, just not rotational ones. Does that make sense? Okay. Good question. All right. Do we have any other questions before we continue trying to solve?
Wait, does this mean like root joints like always become prismatic joints? Because if you try to pick a point on that axis, will do nothing.
Yeah. So they pretty much always act like prismatic joints. The only thing that they're going to affect in reality, like if we were applying this to a real robot, was the number of solutions that we have. So for a prismatic joint, since it's not causing any rotation, we'll usually end up with more reliable solutions, right? But for these screw joints, since they're also causing a rotation, it might have some unintended effects that will leave us with no solutions for that case. But this isn't something that we're concerned about since we're just taking an arbitrary matrix as G design.
So we can treat a screw joint as a prismatic joint only if there's a rotation. And this gives
So not quite. So we're saying that this e to the xi3 theta 3 it's going to take care of both that rotational and translational motion for us. But the fact that some rotation is occurring might affect the number of solutions that we have.
Yeah.
Yeah. So that might end us up in a case where we have like no solution, right? But that depends on the choice of our desired matrix in GP, right? So, but since we haven't actually specified what that matrix is, we're just going to solve it out like that's a problem that we're not having. Right. So we can't apply like a subproblem, right? So those PK subproblems don't apply because we have this revolutional motion and a translational motion now. Yeah, so we're gonna have to come up with some other way of solving this. Yeah, great questions. All right. Okay, cool. So now we're almost where we need, right? We have this point multiplied by this twist on both sides. We know how to calculate this one on the right-hand side. That's great, right? But here's the problem. We still, at the moment, have these two twists left over, e to the xi1 theta 1, e to the xi2 theta 2 that we don't know, right? We can't invert these since we don't know what their values are, right? So at the moment, there's no way for us to bring those over to the right-hand side, okay? So we can't yet invert because we don't know what they are. What they are. Okay, so how are we going to get rid of it? Well, there's another trick that we're going to apply where we subtract a point from both sides, all right? So subtract a point, take the norm. I'm going to express exactly what it is that I mean by this. All right. So, we were just talking about this fact that when we pick a point on, a revolute axis and we apply that revolute motion to that, it's not going to have any effect if it's on the axis, right? So what we're going to do is we're going to actually go ahead and subtract off a point that is on the axes of xi1 and xi2. Okay, we're going to call that point P0. And I'm going to see, or we're going to see why I do this in just a sec. It's actually going to end us up with something very, very nice. Okay, so we have e to the xi1 hat theta 1, e to the xi2 hat theta 2, e to the xi3 hat theta 3 times Pw minus this point that we might not fully understand yet. So P0 equals G times Pw minus P0 on this side. Okay. Now the next thing that I'm going to do is that I know that these e to the xi1, e to the xi2, they're going to do absolutely nothing to this point P0, right? Since this point P0 is on both of their axes. Okay. So they're not going to do anything to it. So if I multiply these two by this point P0, it's not going to have any effect. We're going to have the same equation. Okay. So for that reason, I can write the following. So I would have theta 1, e to the xi2 hat theta 2, e to the xi3 hat theta 3 times Pw minus e to the xi1 hat theta 1, e to the xi2 hat theta 2 times P0 equals G times Pw minus P0, right? And this is the same exact thing that we just wrote above because this point is on these axes, right? It's not going to be, or these transformations here aren't going to do anything. So we may as well include them. We may as well not. All right. But what this will enable us to do is actually factor out an e to the xi1 hat theta 1, e to the xi2 hat theta 2, right? Now we have both of these together on both of these terms. So we can rewrite this as the following. Xi1 hat theta 1, e to the xi2 hat theta 2 times e to the xi3 hat theta 3 minus P0 equals G times Pw minus P0. Okay. So what I've done is I'm taken this transformation, and now since it's on both terms, we did factor it. Yeah. Oh, yeah, thank you. It's my bad. Yeah. Great. Thanks. All right. Okay, cool. So now let's talk about a property of rigid body motion. So we know that rigid motions preserve distance between points. Okay, so if we have like a point like P1 and P2, and they have this distance like D between them, right? And we undergo some sort of rigid rotation, right? Like maybe they rotate around such that like P2 is over here, and now P1 has like swung around, it's down here, right? That distance D will still be the same, right? Because these rigid motions, they're not stretching our body, they're not doing anything crazy to it, right? They're not bending it around. That distance will always remain the same, okay? Now what we see is that in here, after we factor this stuff out, this is now the difference between 2 points, okay? So we now have a difference between 2 points in these parentheses. Difference between 2 points, okay? So we know that the magnitude of this distance, this difference between these 2 points, will be the same after we apply the rigid body transformation Xi1, Xi2 as it will be beforehand, okay? So if I take the norm of both sides of this, right? Since these are rigid body transformations, they preserve this distance in between these 2 points, okay? So that means that this distance is going to be the same as this distance. E to the Xi3 hat theta 3 minus this point P naught, okay? G times PW minus P naught, okay? And this is all because E to the Xi1 hat theta 1, E to the Xi2 hat theta 2 is a rigid transformation. So rigid, length preserving transformation. Okay, so it made no effect on the magnitude of this entire left-hand side. So yeah, sure. So using this method of taking the norm on both sides, we were able to completely knock out these unknowns, theta 1 and theta 2. Yeah. Oh, yeah, sure.
So instead of using a PW,
Oh my gosh, yeah. Keep forgetting the PW. Yeah.
So it's not so the design one,
Yep.
Those are multiplied by the other one, right?
Yeah.
Because like it's all one thing.
Right.
The length of all of that is the same.
Yeah,
So
yeah.
that's why we get rid of the other two because they don't make a difference.
Exactly, yeah. Because this thing, right. So this on the inside is a difference like between points. And that's exactly like what we have in like this little scenario down here. We have like a P1 and a P2. But in this case, it's like E to the Xi3 theta 3 PW might be like our P1 and then P naught. It might be this one over there. Yeah.
I kept on thinking the length of each one. So that's why that's why I was thinking of it.
Oh, okay.
But
Yeah.
that's not right.
Yeah, it's just the rigid body length preserving transformation. Yeah. All right. Do we have any other questions before we continue? How we feel? Good. Yeah.
So are there any cases where we don't have to do correct with my choice? For example, in discussion before the last, yeah.
Yeah, they just jump right to a solution, right?
Yeah, I don't think that's because you know because one of the points chosen is not on the elemental, or like it's on that side.
Yeah, yeah. So in that case, I think something that we had was like, oh yeah, perfect. Thank you so much. All right. So yeah, we had like a rotation about that joint and maybe like another rotation about that joint. And then finally, like we had like a prismatic joint that was coming through like that was able to move like up and down, right? So the reason we were able to jump straight to a solution is that this thing was the only thing that was able to move this entire arm up and down, right? So only thing to move in the Z direction, right? So since it was the only thing that was actually changing the Z coordinate, we were able to jump straight to a solution, right? Because all these other ones, they're just moving us around in this plane, okay? But if we take a look at this arm over here, now all of these other axes that we have are able to move all the other coordinates. So if we just apply this screw motion, right, it's not just potentially going out in this direction, but if this arm moves, it could be going out in that direction, it could be going out in that direction, in that one, so on and so forth. So since we don't know the actual direction that this arm will be pointing, we need to use the method of the norm instead.
I guess just to be safe, we should just use the select out everything because it also
Yeah.
like covers the special things.
Yeah, exactly. Yeah. All right. Okay, do we have any other questions?
Can you show again like how you got to the parentheses, like
Oh, yeah, like this step right over here.
Yeah.
Yeah, so what we did was we picked this point P0 over here such that it was on the axes of this first rotation and the second rotation. So because it was on the axis, we know that those rotations are doing nothing to it. So if we just have this point on its own, that's the same as multiplying those rotations by that point, right? Because it's not going to do anything to it. And then that allowed us to go ahead and factor out this e to the psi hat 1 theta 1, e to the psi hat 2 theta 2 because they appear in both terms. Right.
Just a quick question about the question from discussion.
Yes.
So,
Like this one here. Or,
yeah, so like, I was just thinking, so like, wouldn't the second joint still be able to flip that t-axis?
so
Like,
if it was positioned like this instead, oops, where we think this coming into here, it's over here, and we were able to rotate in that direction, then that would be moving this thing up and down like that, right? But these other ones, it's just like I have my elbow over here and my shoulder over here.
So we have to consider each single one. And
Yeah.
see if it's affecting the anything.
Right.
And then
We can
decide what to do.
Yeah.
So overall, it's just better to just use the.
Yeah, just go straight to the norm and then you know it's gonna work.
Okay.
Yeah. All right, cool. So something really important to mention is that this is not subproblem 3. Not subproblem 3. Okay? It looks a lot like it, and a lot of the things that we're doing are very much inspired by subproblem 3. Yeah. So what we're doing over here is not subproblem 3. Okay? So subproblem 3, remember, is only for the case of a revolute joint. In this case, we have a screw joint, so we also have this translation going on, which means that the solution of subproblem 3 does not apply in this case. Okay? So we're going to come up with our own solution to this problem in just a second. Yeah. I don't know off the top of my head. I know the only ones they have in the book are 1 through 3, but I know on Wikipedia they have flex extras. Yeah. So don't worry about that. Yeah. All right. Fantastic. What's up? It's
The guy called Brad.
Brad, yeah.
oh, Brad. Yeah, Brad Paden. Yeah, what a guy. I'm pretty sure he was Shastri's PhD student.
Oh.
I believe so. Hang on. Let me check. Brad. Yeah. Brad Paden. Let's see if he was. Oh yeah, PhD East Berkeley. Oh wait, and BS East Berkeley as well. So maybe he took 106 in. What's up? So he did his bachelor's and PhD here, the guy that solved these problems. I don't know, this was in like 1990s, I think. So maybe it was just like numerical solutions or something. Yeah. Yeah. All right. Yeah, no pressure, guys. All right, perfect. Okay. So let me copy this most recent picture of it, and then we can go ahead and talk about our solution. Okay. So we have this, let's see, e to the All right, perfect. So at the moment, we're almost there, right? If this was a subproblem 3, we could pretty much call it here and say we're good to go, but it's not, right? We have this screw joint screwing things up for us. Lives up to its name. So here's the problem, right? We have this norm over here. We don't really know what to do with it, okay? We know what the value of this is on the right-hand side. We know this. since we know every single point on the inside, right? We fully understand what the value of this right-hand side is, right? It's just this thing on the left that we don't know how to compute. So what we're going to do instead is we're going to try and figure out geometrically what this is going to be, okay? So let's take a look at what is going on in this case. So we have an e to the xi3 theta 3 times pw minus p0, okay? So let's talk about what these different points are. So p0 equals this point over here, right? It's going to be this point on these axes. So it's the point on xi1 and xi2, okay? And what e to the xi3 theta 3 is it's the position of the wrist after we rotate it and translate it by this distance, or excuse me, by this amount theta h times theta 3, okay? So it is the wrist position after moving along xi3 by the pitch of the screw h times theta 3. Now it's really important to remember right here, it's not theta 3 directly because this is a screw joint, okay? This is where that one difference between screw and prismatic joints comes in. If this was a prismatic joint, like it was in the homework, we would just directly take that theta 3. But since this is a screw, we need to include that pitch. If we give you h equals 1, then you could just plug in theta 3 and you're good to go. But here we've just called it an arbitrary, an arbitrary pitch, okay? So what is this distance going to be? Well, let's think about a couple different cases, okay? I'm just going to sketch this out in a simple form over here. So we have our point P0 and we have our wrist point PW, okay? So we know that before we've actually moved, what's the distance between these two going to be? Well, we know that's just going to be the length of the arm, right? That's L1. So it's starting off at L1. Now, after we move it by a certain amount, right, we know that that new amount will be h times theta 3, okay? So then our overall distance from all the way on the end here to this amount, what's that going to be? Well, our overall distance is going to be h times theta 3 plus this extra distance L1 that we started at, right? That's because we're starting over here at PW, which is already at L1 with respect to P0, and we're moving forwards along this direction, okay? So as we change this value theta 3, the position of our wrist, the amount that this will have moved with respect to this original point P0 will be h times theta 3 plus L1, okay? So when we take a look at this norm up here, that's exactly what we're doing, all right? We're taking the distance that this wrist has traveled right over here, and we're just subtracting off that point that we started at, P0. And right here, we've just come up with a formula for what that distance is, right? It's this h times theta 3 plus this L1 that we were starting at, okay? So this is exactly equal to this norm that we have up here, all right? So what I'm going to do is I'm going to plug in h times theta 3 plus L1 equals this norm that we know the value of, g times pw minus p0. And now I'm just going to solve for theta 3, okay? And what we're going to end up with is theta 3 is this norm, g times pw minus p0 minus L1 divided by the pitch h, okay? And that gives us a single value.
How did you get the GPW again?
Oh, so this GPW is just what we've been carrying down this entire time on the right-hand side. So yeah, that's the right-hand side of our equation. So it was like this guy over here. So we just found an alternate formula for that. We just right. Yeah, and this is something that we know the value of since we've already calculated all those terms. Yeah. All right. So then all up, we end up with a single value for theta 3. Okay. So there is one solution that we've come up with on our own. Yeah. Yeah, so it's the amount that it rotates, not the amount that it translates. So h times theta 3 is the amount that it translates. Right. So if we just want to convert this into a prismatic joint, then we just get rid of this h from here. And like that would be our theta prismatic. Yeah. All right, cool. So that's how we solve for the case of a screw motion right here. Basically, we just start out by treating it as prismatic. We just ignore any problems that are going to happen with the rotation. We say our twist xi3 is going to take care of all that stuff for us. Right? We don't need to worry about it. And then we just go through and we come up with this closed form solution for theta. Yeah.
Is it possible for this to have two solutions? Because the thing that like slightly confuses me is we're saying two norms being equal to each other, right?
Yes.
So could it not be in the other direction? Or is that?
Oh, I see. Like if you're going to the other side.
Yeah.
I think in this case, since we're specifying that it's starting at L1 and like the prismatic joint can't go backwards past L1, I think it would end up being restricted to this case because I think we have 0 is less than theta 3 is less than d max or something. Yeah. Yeah. Sure. Yeah. Yeah. Tell me when. Okay.
Someone put something in the chat too. When I
Oh yes. Let me see. So will we ever need to solve a case where there is an arm coming off of the screw? Yeah, you might. Yeah. So in that case, you'll have to do a little bit of trick to figure out what's going to happen. We can do a problem like that right now if you want.
Yes, that would be nice.
Okay. Cool. All right.
Wait, okay, the screen big passes. Oh, wait, you said this is an H, territory plus L1 is P naught.
So it's equal to this entire norm over here on this right hand side. So this was this.
Because I was looking at where you drew.
Oh,
the entire thing.
It's the entire thing. It's the entire thing. Yeah. Sure. Yeah.
Wait, they're saying like the arm is literally affected.
Yeah, like it's moving towards you. You don't think of it like it's gonna fall off at some point.
Yeah.
Or something. Yeah. It's all good. Yeah.
So I got a bearing on it.
All right. So how do we feel about this one like all together? Was that okay? Does that make sense? Okay, sweet. So do you guys want to finish this problem out? Because the rest of it is just going to be the same as the homework, or we could try one other screw joint and then okay. What's up? Oh yeah, of course. Yeah, so that's actually that was the second hard example that I had written down, which is nice. So I'm glad it worked out that way. No, what are you talking about? I don't know. Okay, let's see. So we have a screw joint problem 2. All right. I'm going to draw the screw joint first, actually. Let's see. So something like that. This direction. Okay, and then what I'm going to do is I'm going to put the screw as this axis right over here. So this is actually translating the rest of this arm along with it. So now in this case, we have this whole arm that's attached to this screw joint over here. Was this the case that you were asking about in the chat? If you're still there. Maybe. Okay. Jackson, yeah. All right. Okay, cool. Let's see. Yep.
What direction?
So it's going to move like into the page like that. So our screw rotates, this whole arm is going to shift backwards like that. Yeah. But also, we also have this other joint over here that's able to rotate in that direction. So maybe this is something that we'll need to take into account. We'll see. We'll see. All right. I don't know. Anything could happen. All right. So I'm going to call this point over here. Yeah, let me call this P. And stay consistent with my notation here. Okay. Let's point Q. And then just to make it easy, we're going to say that the spatial frame attached. Okay, great. So do you guys have any questions just about like the geometry of this thing before we set off on this problem right here? So we have a theta 2, we have theta 1, theta 2, and a theta 3, and psi 1, psi 2, and psi 3. So just to clarify, screw joint right here is going to be joint 2, all right? And we say that it has a pitch H. So do we have any questions about this setup? What's happening there? Yeah. Yes. Yeah, exactly. Yeah, so this is sort of, I don't know, you can think of it like tracing on a helix in space as it's going by. So it's like, I don't know. So yeah, so this thing down here is able to rotate. So if we froze that and then we just move this other one, we would be moving backwards in space and tracing out. So we would get like this helix pattern going through.
Can I show you what I have?
Yeah, sure, please.
This helps me understand it.
Okay. Yeah, that looks good. Yeah.
Okay.
Yeah. Yeah. Yeah, that's a good idea.
We can pass it around. I don't get the best.
Yeah, here, let me
understand.
let me draw it the way you did, because that looks good.
Oh, I see it.
Yeah, so it's like we have the rest of our robot arm attached right there. Xi2 is our screwdriver.
Like this. Me too. I feel like this. Yeah. Because it's thinking.
All right. So can you guys sort of picture what's happening with the screw joint here?
Yes.
Okay, cool. Yeah, thank you for the picture. That was great. Yeah. All right. So what are we going to do? How are we going to tackle this whole thing? All right. So once again, we're going to do the screw motion first. Screw motion first. Okay. So just remember that this is something that we do because we always know that these screw motions or prismatic motions, whichever ones they are, as long as they have some amount of translation, they're going to be giving us this really sort of unique motion that these revolute joints will not. So maybe that'll make the solution process easier for us. Okay. So let's give that a go. First out, I'm just going to lay out my product of exponentials formula, just like before. Okay, so we start product of exponentials. And what we're going to do is we're going to do e to the xi1 hat theta 1, e to the xi2 hat theta 2, e to the xi3 hat theta 3 times our initial transformation, GST of 0, is equal to our desired rigid body transformation at GD. Okay? So I'm going to start out just by doing that same thing that we did as last time. We're going to isolate all of these angles over on the side. All right. Okay, so I'm going to multiply both sides by the inverse of GST of 0. So I'm going to do GST of 0 inverse. I would also be multiplying that right there. I'll just save us the time and then just write it like that. All right, cool. So once again, I'm just going to call this G just to make it easy for our bookkeeping purposes. Okay, so now we have e to the xi1 theta 1, e to the xi2 theta 3, e to the xi3 theta 3 over here. So what are we going to do about this, right? At the moment, we're in our same situation that we were in this last problem, right? In this previous one, where we had that problem where we have this xi1 and xi2 in there, right? We want to get rid of it. So let's see if we can figure out how we can do that same thing where we did this like trick with the norm last time, okay? So what can we do first? Well, we know that we want to get rid of like the xi3 theta 3 somehow. If we want to be able to solve for the amount that this other guy is moving, right, along that axis. So what we're going to do is we notice that in this case, this is a purely revolute joint, right? And that's great because we know how to knock out revolute joints, right? We know if we multiply a revolute joint by a point on its axis, we'll be able to drop that revolute joint entirely, okay? So I'm going to multiply both sides by this point P, which I've chosen to be on this axis, okay? So that's going to leave us with e to the xi1 hat theta 1, e to the xi2 hat theta 2, times e to the xi3 theta 3 times P equals G times P on this side, all right? And we know that since this point P is on the axis of e to the xi hat 3 theta 3, it's doing absolutely nothing, right? So it may as well not be there. So let's end up with that, okay? Let me go ahead and move this over as well. Okay, great. So now next up, we see that we have our screw joint, right? Theta 2 right here. But we still have this theta 1 that's sort of in the way, right? Kind of a pain, we got to get rid of it. So we're going to do this trick with the norm that we did last time to get rid of this other transformation, right? Remember, we had that property where we know that rigid body transformations preserve the length between different points, okay? So what can that second point be that we choose? Well, something that might be good is something like this point Q over here, right? This is a very easy point for us to imagine. It's just a 0, 0, 0. So why don't we go and subtract off this point Q from both sides? Okay. So e to the I1 half theta 1, e to the I2 half theta 2 times P minus Q equals G times P minus Q. And the most important thing about this point is that it's on the axis of psi 1, right? Yeah.
Can we choose a point to be there from the axis of psi 1 and not on that 2?
Yeah, so we could choose it like down here, and that would work fine as well.
Okay, doesn't matter. It's not-
Yeah. So another nice reason about this is that this frame right here, I've defined to be like right at that point. So this is essentially like the origin for us, which will make our math a little bit easier a little later on.
Yeah, so subproblems are to one.
Yeah. So the thing is that Xi2 has both a rotation and a translation. So it'll also just be moving this point along its axis. Yeah. Yeah, great. All right. So once again, we know that since Xi1 is doing nothing to this point Q, right, this is just the same thing as multiplying e to the Xi1 half theta 1 times that point Q, right? Exact same thing. So now we have this e to the Xi1 hat theta 1 on both of these terms. I'm going to go ahead and I'm going to factor it out, all right? This should be seeming a little bit familiar from what we did last time. A lot of these similar patterns will be coming up in all of these inverse kinematics problems, okay? So really, there's only these two tricks. One of them where we subtract this point on the axis, use the norm to knock it out. Those are for the ones that tend to happen on the front. And then the other one, these ones that are like towards the back that we want to get rid of, we just choose a point on those axes and we try to knock them out that way. Okay, so e to the Xi1 hat theta 1 times e to the Xi2 hat theta 2 times this point P minus this point Q equals GP minus Q. Okay? Yeah. Oh, yeah. So like pattern one is if we have a transformation on the front to get rid of. So like to the left of this one that we want to be focusing on. So for example, like e to the Xi1 theta 1 is at the front of this whole thing, and we want to get rid of it somehow. Yeah. So on the front, we try subtracting a point, and then take the norm, okay? And then pattern 2 is for transforms towards the back. Like something like this e to the Xi3 theta 3. That's when we try to apply a point on the axis to both sides. Okay? So apply a point on the axis to knock out. Okay, great. So at the moment, what we have is we have this rigid body transformation, e to the Xi1 half theta 1 times the difference between 2 points. Okay? So I'm going to take the norm of both sides, and I'll just review why that is once again. All right. So once again, we know that these rigid body transformations, they're going to be preserving the distance between 2 points. Okay? So this one right here, that's a point. This one right here is also a point. So we know that when we apply this rigid body transformation, e to the Xi1 theta 1, the distance between these 2 points will remain the same. So this magnitude is actually equal to the following. Xi2 half theta 2 times this point P minus this point Q equals G times P minus Q. Okay? And once again, we were able to do that because this Xi1 is a length-preserving rigid body transformation. It's never going to be changing the distance between those 2 points. Okay, so does anyone have any questions about like that stuff? Sure.
So GP.
Yes.
And E but I2 and
Yes.
those are not equivalent to each other.
No, those aren't equivalent to each other. So this GP was this thing that we had defined like over here, this GD GST inverse of 0 times G. So we're going to be trying to find something to get these the same. But the point is that I want to make here is that we're taking the norm of both of these sides, and that's what's making it look like they're the same thing.
Yeah, but like I know that they're not the same.
Right.
But it's just that like because like they equal each other.
Yeah.
Like, I just
and then 2 minus 5. Norms on both sides. So 8 is not equal to 2.
Yeah, that's a good counterexample right there. Yeah, so it's just because we're taking this norm that we were able to drop this e to the side 1 theta 1, e to the side 2 theta 2. And then we're just left over with this instead. Yeah. Okay. So we're now pretty much ready for the same step of geometric interpretation that we started with last time. Okay. So we've knocked it down to one norm. Knocked down to one norm with one transformation. Okay. We only have this transformation left that we want to focus on. We're pretty much where we want to be. Okay. So to figure out this actual value for theta 2, what we're going to do is we're going to try and geometrically interpret what this transformation is doing. Okay. So e to the xi2 hat theta 2 times a point p. What will this do to p? What will this do to p? Okay. Well, we know that, first of all, it's going to be sort of like rotating this point p in space, right? It's going to rotate a little bit. And second of all, it's going to be like translating this point along this axis as well. Okay. So it rotates and translates your point P in space. Okay. And this minus Q, well, that just gives us our distance to our origin of our coordinate frame. Okay. So what this is equal to is like e to the xi2 hat theta 2 times P minus the 0 vector 0, 0, 0. Right. Since we just put Q like right on the origin over there times GP minus. Oh, I think I was meant to let my friend into Corey. Oh no, it's gonna be an 8. Awesome. Okay, good. So we have this e to the xi2 theta 2 p minus the 0 vector. We know the 0 vector will have no effect on this norm, right? So we may as well just drop that out. So e to the xi2 hat theta 2 times the point p is equal to the norm of gp minus q. All right. Now this is a single point, right? So we're translating it in space. Since this isn't the difference between 2 points, this is no longer length preserving, right? This is a physical translation where we're physically moving this point, right? So we can't get rid of this e to the xi hat 2 theta 2. So it actually becomes kind of complicated in this case to solve for what's happening. Yeah.
Like, why doesn't the left hand side Q also go?
Oh, yeah, that does.
And this is because Q was the origin, not like plugging something.
Yeah, exactly. Yeah.
And just from Q's origin.
Yeah, so Q is the origin, and we just put P right there at the intersection of these axes. Okay, so let's see if we can figure out what this point P is. So this will be the first time that I'm doing this actually, which is kind of fun. So we'll see how it goes. All right, perfect. So the first thing that we're doing is we are rotating about this axis by an angle theta, right? So what we're doing is if we look at this axis straight on, where this axis is going directly into the page, we knew that we were taking theta in this direction, right? So if we have our point P, like at the 0 position is all the way out there, right? We're going to be rotating it around like this, okay? So our theta is actually coming up in this direction, this theta 2, all right? So that's the first thing that it's doing, is it's rotating it about this origin. So how do we actually figure out where this point is going in space? All right, well, let's see what that might be. So we know that this distance right here is going to be the norm of this vector P, right? Because that's going to be the same distance as it was from here to here, right? We're just taking this thing and we're moving it around. Now we can use trig to figure out what the different components of this are going to look like, okay? So remember that this was our z-axis pointing up, and this was our y-axis, right? Like if we look at this frame over here, we're really just looking at like this revolution, or just extend it out to point P. Okay, so the circle that we're interested in is that. All right. Then we're going to figure out the depth of it later on. Yeah.
Why do we want to?
Oh, yeah, that's a great question.
You know, sometimes we might not have that.
Right. So in that case, I place the origin right here to make this math a little bit easier on us. But otherwise, you would be subtracting off the point. Like if this was your length L naught, you could subtract off the point 0, 0 L naught. And then you would have to include that in your norm calculation as well. Yeah. Okay, cool. So let's figure out where this thing is going, right? So first of all, we're just looking for the z and the y coordinates. We use trig. We see that this length of this right here is equal to, what's that going to be? Yeah, so that is sine of theta 2 times the norm of your vector p, right? And that this little length along this guy right over here, that is equal to the norm of p times the cosine of theta 2, okay? Oh, I think they're coming later. Yeah. Okay, so we have a cosine on one, we have a sine on the other, right? That's just from doing like the dot product right there, or just using basic trig. Yeah. Yeah, I'm just talking about the length of this at the moment. Yeah. So if we look at our actual z coordinate, it's going to be negative magnitude of p times the sine of theta 2, and our y coordinate is going to be the magnitude of p times the cosine of the angle theta 2. Okay. So we got that. We have our last two components of, this vector like e to the psi 2 hat theta 2 times p, right? We now know that this is just our y coord, our z coord, and x is still unknown, right? So what do we know about our x coordinate? We know that our x coordinate is coming from the translation of this screw, right? The screw is oriented facing backwards, like into the page, right? Like it's going into the board. So what is the translation of that going to be? Let's take a look at our picture. And we know that the x-axis, the positive x-axis, is pointing out this way, right? So by the right-hand rule, if we're going inwards in the page, we're going to have every translation happening, or for a positive theta, we're going to have our translations happening in the negative x direction, okay? So we give the amount of translation by the pitch of the screw, h, times the amount that we are rotating, theta 2, okay? So we know that we're going backwards by a distance h theta 2 into the board for every theta 2 that we're rotating, okay? So that gives us our total points back into page. Okay, so then we have our total point e to the psi 2 hat theta 2 times p, and that is going to be negative h times theta 2 for our x coordinate, because that's our translation back into the page. Our y coordinate is going to be this thing that we saw for here. So that's going to be the absolute value of, or excuse me, the magnitude of p times cosine theta 2. And then our z coordinate is going to be negative magnitude of p times the sine of theta 2. All right. So all that we need to do now, I know I've been saying all that we need to do for a little while, but what remains at this point is we need to take the magnitude of this vector, now that we found its value in terms of theta 2. We need to equate it to this, which we could just treat as a constant, and then we're going to solve this out for theta 2, okay? So what is the magnitude of this vector right here? Well, did you have a question? Sorry, or were you just scratching your head? Okay. My bad. All right. So if we want to find the magnitude of e to the psi hat 2 theta 2 times p, what's that going to equal to? Well, yeah, so I'm thinking in this case, we might actually, yeah, let me just square this on both sides to make this easy for us, times magnitude of gp squared. All right, so then that way we're just going to be able to drop the square root. It's going to be kind of nice. All right, so we're going to have negative h times theta 2 squared plus the magnitude of p times cosine of theta 2, also squared, plus the negative magnitude of p sine of theta 2 squared equals magnitude of gp squared. Okay, so the square of negative h theta 2 is h squared theta 2 squared, right? Then this is going to be plus magnitude of p squared cosine squared of theta 2 plus the magnitude of p squared, because that negative will drop out, times the square of the sine of theta 2 equal to gp squared. Okay, so now what we're going to do is we're going to go ahead and factor out this magnitude of p squared, cosine squared of theta 2 plus sine squared of theta 2 equals gp squared. So what can we do to simplify this in this case? Does anyone notice anything? 1. It's 1. Yeah, so this is the Pythagorean identity right here. Okay, so we can knock that whole thing out, and that leaves us with only one theta 2 squared term remaining. h squared theta 2 squared plus the magnitude of p squared is equal to the magnitude of g times p squared. All right, so I'm going to bring over this p squared over to this side, and then we're going to go ahead and solve for our final value for theta 2. Okay, so we're going to end up with theta 2 equals, I'm going to write the square root afterwards. So it's going to be norm gp squared minus norm of p squared over h squared square root. All right, and plus minus that. So then that should be our final value for theta 2, I think. And yeah, that about does it for that problem.
Do you like think that if it's like large things go, or it's like kind of takes for a while?
Something like this could be on the midterm. Yeah. You guys will be fine. It'll be okay. Yeah.
So that's what you give us the identity of
Yeah, maybe. I don't know.
But you know, about 15 people know how to do it.
I'll see if we should break the curve. Break the curve.
Yeah. So what's up? Yeah, the classes curve very generously, so you don't need to worry about it. Yeah. Same. Yeah, you guys will be fine. All right. I think I will probably leave it there for the Zoom recording as well. Thank you guys for showing up.